morning, guys. Welcome to the class of CE331 Environmental Engineering 1. So we were discussing from the last class disinfection, right? And we saw different methods of disinfection here. So one of one of the most popular methods of disinfection is adding chlorine in different forms. That's called chlorination. Okay. So what happens that when you add chlorine to water, when you add chlorine to water, it forms hypochlorous acid, hydrogen ion, and chloride ion. And this HOCl here, you can see this produces what? Basically hydrogen ion. Since this is an acid, it produces hydrogen ion and hypochlorite ion. So this hypochlorous acid, HOCl, this, I'm referring to this, and hypochlorite ion, these two are basically kills the uh, pathogens. That means they acts as a disinfectant. Okay, and we call it free chlorine, free or available chlorine. We call them free or available chlorine. Okay. What are the two agents? Hypochlorous acid and hypochlorite ion. Okay. And if you add chlorine in water, which form it will be found, it depends on the pH of the water. As you can see, with changing in pH, the species concentration changes. For example, from 0 to 2, I would say maybe 1, okay, chlorine concentration is the most highest. However, HCl and OCl, I mean hypochlorite ion, are the lowest concentration. On the other hand, from 4 to 6 in this range, you have the highest concentration for HCl. Guys, are you following me?
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
However,
sir.
chlorine and hypochlorite ion concentration is low. And if you go beyond 9, you'll find that hypochlorite ion has the highest concentration. At which around 7.5, you'll see this both curve meets. Okay, that means the concentration of hypochlorous acid and hypochlorite ion are equal. Okay, similarly here. So now the thing is, our objective is to kill the pathogens, right? Now,
Yes, sir.
when you add chlorine here in different forms, you are expecting that chlorine will directly produce HCl and hypochlorite ion, and basically, sorry, you're expecting that they will directly kill the pathogens, but some portion of chlorine does not directly kill pathogen because of wastage. How does this wastage comes in? You have impurities in water. This is wastewater, am I right? This is wastewater.
Yes, sir.
Or water, it has organic matters. Now, if you have pollutants in water, what happens that this species reacts, or chlorine reacts with the pollutants and produces something else, and you don't get them. Therefore, some of them is lost. I'm repeating again. When you add chlorine, and if you have pollutants in water, that chlorine, some portion of the chlorine reacts with the pollutants and does not give this, produces something else. Therefore, some chlorine is lost. For example, if you have ammonia in water, this pollutant, the hypochlorous acid reacts with them, replace one chlorine from here, three hydrogen, right? One hydrogen is replaced with chlorine. Did you see here? One hydrogen is replaced with chlorine. Can you see this?
Yes, sir.
So this is one chlorine, so monochloramine. Again, this species react with another hypochlorous acid and replace one hydrogen ion again with chlorine. Now you can see there are two chlorines, so it's dichloramine. Okay, and similarly, this dichloramine I'm referring to this species reacts with again with hypochlorous acid and produces trichloramine, and it happens at different pH range, as you can see. Okay,
Okay, sir.
also which species will form that depends on the ratio of chlorine to the nitrogenous matter. I mean, how much pollutant you have in water with respect to the chlorine. Is it clear? Is it 1:1 or is it 1:5, 1.5? Okay, so it depends on the constant. We'll see. We will discuss it in later in the next stage. Okay, fine. So this reaction can also happen. Okay, now look at these equations. Here you have, what do you have? Here you have monochloramine. Here you have dichloramine. Here you have trichloramine. Am I right?
Yes, sir.
Now, among these three species, only monochloramine, this one, and monochloramine, this one, and dichloramine, this one, they act as disinfectant. But this trichloramine does not work as disinfectant. That means this is a lost wastage of chlorine. Am I right? In terms of disinfection, because this chlorine does not work as a disinfectant. So this is lost. This amount of chlorine is lost, right?
Yes, sir.
That's why they're telling here that the mono and dichloramine have significant disinfecting power and are therefore interested in the mechanism of chlorine residuals. So they are called chlorine residuals. Okay. Now, total chlorine residual is our interest because chlorine residuals are the species which act as disinfectant. Now, who are they? First of all, they are free chlorines, which are disinfectant, as I told it before, hypochlorous acid and hypochlorite ion. Okay, and then combined residuals. For example, monochloramine here and dichloramine here. However, the trichloramine, which is NCl3, does it work as a disinfectant?
No, sir.
Trichloramine? No. So it will not come here. It will not come here. Okay. So your chlorine residual is basically free chlorine and the combined chlorine. And combined chlorines are basically the monochloramine and dichloramines. That's it. Okay. Okay. Now we have discussed only about the nitrogenous matter or pollutants here or impurities here. Chlorine can also react with other species. For example, if you have iron, manganese, nitrogen dioxide, hydrogen sulfide, these species in water, they can also react with chlorine, and as a result, chlorine is lost or wasted. So that's what they're telling, that chlorine combines with various reducing agents and organic compounds and therefore increasing the chlorine demand, which must be satisfied before chlorine is available to accomplish the disinfection. Here you got a term that is chlorine demand. We'll see what is this. This is important. Okay, now chlorine can react with phenols to produce mono, di, and trichloorophenols, which can impart tastes and odors to water. Chlorine also reacts with humic substances. This is a kind of organic matter also present in water to form trihalomethane. Now, this is a problem. THM, trihalomethane, like chloroform, bromoform, which are carcinogenic. Did you see carcinogenic? Do you know what is carcinogenic? That causes cancer.
Yes, sir. That causes cancer.
Yeah, so that's the problem. So your chlorine dose must be in such a way so that it does not produces these trihalomethanes. Okay. Now breakpoint chlorination. So what we have discussed here is that in pure water you have pathogens. You added chlorine. For example, you needed for this 1 liter water, you needed 5 gram chlorine. Now in a water, same amount, 1 liter. This was also 1 liter. Okay, same amount of pathogen, okay, same concentration, but you have additionally pollutants here, other impurities here, for example ammonia, nitrogenous matter and other matters. Now what will happen here? The requirement of chlorine will be higher than 5 milligram per liter, or less than 5 milligram per liter, or equal 5 milligram per liter. Tell me.
Sir, higher.
Higher. Why? Because some portion of the chlorine will be wasted to react with this red color I have indicated with these impurities. And impurities are, as I told you here, like nitrogenous ammonia, okay, and other matters like this iron, manganese. Okay, so the chlorine requirement with impurities will be higher than that what would have been required in the water which does not have the impurities. So here for example you needed 7 gram. So how much wasted, guys? How much chlorine is wasted?
2 grams.
7
2
minus 5,
gram.
that is,
2 gram.
this chlorine did not take part in disinfection, by the way. This chlorine did not take part in disinfection. This is wasted, and this is called chlorine demand. How much chlorine you require to neutralize the pollutants before the chlorine start acting as disinfectant. So this is called chlorine demand. Okay, is it clear, guys?
Yes, sir.
Fine. Now we need to know how much chlorine you need to add. Okay, and we can do this by testing it in the laboratory. We will do this inshallah. So what we do here is this: in different sample, one, two, three, four different sample, we take different amount um, of chlorine dose. We put different amount of chlorine dose, and in this graph we plot a graph which looks like this. Here in x-axis we put the chlorine dose, milligram per liter, and here chlorine residuals. Again, what is chlorine residuals? Chlorine residuals is free chlorine.
Mono.
Yeah, first of all, free chlorine and monochloramine and dichloramine. Basically, chlorine residuals are the products which acts as a disinfectant. Okay. Now, first of all, first of all, if you have impurities in water, if you have impurities in water, so what would happen? Chlorine will react with the impurities. chlorine will react with these impurities and produce something else rather than chlorine residual. So you will not get any chlorine residuals. You will not get any chlorine residuals. So therefore, what does that mean? That means that you are adding chlorine, but you are not getting any chlorine residuals. So the curve will be like this. Am I right? Zero, zero y-axis,
Yes,
and
sir.
up to this, for example, we have added up to this chlorine, and you see there is no y, there is no rise in y-axis direction. Chlorine residual, chlorine residual, no chlorine. So this is first of all this, right? Now, now you start producing monocloramine and dichloramine. And are monocloramine and dichloramine part of chlorine residual? Yes. So now it starts increasing. Are you following me?
Yes, sir.
Yes, sir.
So let's see what they're telling here. A. If the water is free of ammonia and other compounds that may react with এটা পরে আমরা পড়বো এর বি থেকে শুরু করি chlorine first reacts with reducing agents such as hydrogen sulfide, iron, manganese, and develops no measurable residual as shown by the portion of the curve from the origin up to point A. From the origin up to point A, zero. Clear?
Yes, sir.
Yes, sir.
Yes, sir.
Now C. Addition of chlorine beyond point A. So beyond point A in forming mainly mono and dichloramines with mole ratios of chlorine to ammonia up to 1 is to 1. That means when your ratio of chlorine is in this range, for example, um, chlorine divided by ammonia, this ratio, molar ratio is 1 is to 1, 1 is to 1, or you can write it in this 1 is to 1, then it produces mono and dichloramine in this range. Is it clear? So
Yes,
you
sir.
have chlorine
Yes,
and
sir.
ammonia nitrogen, yeah, okay, that's why you can call nitrogen ammonia nitrogen 1 is to 1. So mono and dichloramine are formed. Chlorine thus formed are effective disinfectants and therefore are shown as combined available chlorine residual in figure from A to B. So from A here, from A, let me, this is from A to B. So what is happening here? Formation of chloroorganic and chloramine compounds. Chloroorganic and chloramine compounds. Which range? A to B. Clear?
Yes, sir.
Chloramine compounds, they are referring to monochloramine and dichloramine. Here, by writing chloramine compounds, they are referring to as monochloramine and dichloramine. Okay, and other chloroorganic compounds. Fine.
Okay, sir.
Now, beyond point B, what happens? You have added more chlorine beyond point B. Am I right? You're adding chlorine. Now, what happens that this ratio now
Yes, sir.
here, this ratio becomes 1 is to 5 because you have added more chlorine and ammonia nitrogen has some part of it has been destroyed by the previous chlorine. Now you have added more chlorine and you are going beyond point B and therefore your 1 becomes 1 is to 1.1 is to, I'm sorry, this is 1.5. 1.5 is to 1. That means chlorine ratio is 1.5 and ammonia nitrogen is now 1, which has increased.
Chlorine.
Chlorine. Relatively, chlorine concentration now is higher. Now, if chlorine concentration now is higher from B to C, what will happen? Now, your monochloramine and dichloramine, now they will convert to trichloramines. The monochloramine will convert to now trichloramines. So your chlorine residuals, which were mono and dichloramine, sorry, for dichloramine, they are now converting to trichloramine. Now, is trichloramine part is a is trichloramine a part of the chlorine residuals? No.
No, sir.
So therefore, you can see that beyond point B, your concentration is decreasing. Am I right?
Yes, sir.
So beyond point B, as you can see, your concentration is decreasing. Is it clear? Why? Because here you had monochloramine and dichloramine. Okay? But here, due to the changes in the ratios, these monochloramine and dichloramines now are converting to what? Trichloramines, which is not a part of chlorine residuals. Okay, which is being transferred to chlorine residuals, and that's why they are not part of chlorine residuals anymore, and that's why they are decreasing. Is it clear?
Yes, sir.
Yes, sir.
Now, up to point C, all the impurities in water has been completely transformed by the chlorine. Now, at point C, you do not have any impurities anymore. Is it clear? So therefore, what would happen? As you increase chlorine dose, you will get all of them as chlorine residuals because you do not have any impurities. If you don't have any impurities, then whatever you give, you get it. There is no wastage anymore. Is it clear?
Yes, sir.
So in B to C, they're writing it as destruction of chloramine and chloroorganic compounds. Destruction of chloramines and chloroorganic compounds is decreasing. Now at point C and beyond, you do not at point C and beyond, you do not have any impurities anymore because all of them have been destroyed by the chlorine. Now, whatever you add beyond point C as chlorine dose, you will get them directly. There is no wastage anymore. So that's why you get it directly 45-degree line. Whatever you give, you get them. Is it clear?
Yes, sir.
Yes, sir.
So that's why they are writing formation of free chlorine. Now you're getting free chlorine because you do not have any impurities. Whatever you get chlorine, you are getting HOCl and OCl minus. I mean hypochlorous acid and hypochlorite ion. And presence of chloroorganic compounds not destroyed. Here, some part of it is not yet destroyed. So they are still present here. Is it clear?
Yes, sir.
So at point C, you had combined residual, and if you are here now, so here total chlorine residuals is some part of it is combined residual and some part of it is free residual. Okay, combined residual means monochloramine and dichloramine and free residual. Is it clear, guys?
Yes,
Yes,
sir.
sir.
So that's it. So addition of chlorine beyond point C would produce free chlorine residuals and is referred to as breakpoint chlorination. So this po- point C is called the breakpoint, because at this point all the impurities has been destroyed. Okay, so if you achieve this point C, this is breakpoint, and whatever chlorine you add beyond this point C, that's called breakpoint chlorination. Okay, so in other words, chlorination of water to the extent that all ammonia is converted to nitrogen or higher oxidation state is referred to as breakpoint chlorination.
Sir.
Yes, go ahead.
Sir, is chlorine residual and free residual are same?
Look at this. Chlorine residual is a combination of free chlorine residuals as well as combined residuals.
Oh, okay, sir. Okay, sir.
This equals to plus this plus this. Is it clear? So
Okay.
chlorine residuals are both
Yes, sir.
free
Clear.
chlorine and combined residuals. Okay, basically these are acting as an as a disinfectant. Clear?
Okay, sir. Yes, sir.
Environmental.
सर ब्रेक पॉइंट टारगेट
Okay, so
मुझे
breakpoint is basically the point C where all the impurities, basically all the impurities has been destroyed. So if you don't have any impurities anymore, so whatever you give, you'll get it. Whatever you give, you'll get it. Is it clear?
ओके सर
Now, if you take a sample of water which has only pathogens, no impurities, then what would happen? What would happen? From the very beginning, from the very beginning, at this point C, you will get a 45-degree line. Whatever you give, you get it. Whatever you give or add as chlorine, you get it as chlorine residual. Am I right? Because you don't have any wastage.
यस सर
You don't have any wastage here. So this is a water which does not have any impurities, and we call this line as zero demand line because you do not have any demand for chlorine. You know what is demand? Remember, demand is the wastage. Do you have any wastage for a pure water with only pathogens?
नो सर
No. So this is zero demand line. So you do not have any demand. So this is called zero demand line, which has been referred to as here, right? Carved for water with zero chlorine demand. Which one is this? This one. Okay. Dashed line. This dashed line. This is the chlorine demand, and it will be 45 degrees. Whatever you give, you will get it. If you at this point, for example, you gave how much? One. You get how much? One. Clear? At point
Yes, sir.
C, you
यस
you
सर
give two, you get two. Okay. So that's all. Any question, guys? Okay, so environmental significance. So breakpoint chlorination is required to obtain a free chlorine residual for better disinfection if ammonia is present in a water supply. While free chlorine residuals have good disinfecting power, they are usually dissipated. Dissipated means escape. Dissipated means escape quickly in the distribution system. Now what they're telling is this.
Sir.
Yes,
Sir, when the chlorine dose is 5, we are getting 3 in the graph.
when chlorine dose is 5, we are getting 3. Exactly, you're right. Because some part of it has been destroyed,
Yes, sir.
right? So it is a chlorine, it is a water sample which has impurities and which therefore it has chlorine demand. And chlorine demand means chlorine wastage. So you
Yes,
got
sir.
you give 5 and you get 3. That means what is the wastage? 5 minus 3.
Yes, sir. 2.
Chlorine demand. But still you have the impurities here. But at this point, all the impurities has been destroyed.
Okay,
Clear?
sir. Yes, sir.
Basically, chlorine demand will be here. At this point, chlorine demand will be 7 minus maybe 1. Am I right? 7 minus 1. So 6 milligram per liter. Am I right?
Yes, sir.
Okay. So what I was trying to explain here is you have disinfectant as both chlorine residual and combined residuals. So you have chlorine residuals. This hypochlorous acid and hypochlorite ion, as well as the monochloramine and dichloramine, acts as disinfectant. But the problem is, although they are good disinfectant, this HOCl and hypochlorite ion, in water, they are highly reactive. They escape very quickly. They escape very quickly, reacts with other things and dissipate quickly. So therefore, they are not stable. Okay, so we try to convert into these species because they are more stable in water, remains in the water for a long time. Okay, so we try to get the chlorine as monochloramine and dichloramine for disinfection because they are more stable. For this reason, the final treatment with ammonia is often practiced to convert free chlorine residuals to longer lasting combined chlorine residuals. Are you following this? Free chlorine residual is what? Hypochlorous acid and
Uh,
hypochlorite
uh,
ion.
I,
Two longer lasting combined chlorine residuals. What is combined chlorine residuals? Monochloramine and dichloramines.
yes, sir.
Okay. And the difference between the amount of chlorine added to the water and the amount of chlorine residual available at the end of a specified contact period is termed chlorine demand. I already told you that at this point, for example, at this point, the chlorine demand is 5 minus 3. At this point, the chlorine demand is 7 minus 1. Am I right? Is it clear, guys?
Yes, sir.
Okay. So remember what is chlorine demand. Understand this very well. Okay. Okay. The use of combined chlorine as disinfectant has been encouraged by evidence that flea chlorine residuals contribute. You know, there is another problem of this. There's another problem of this. The problem is they are more susceptible to produce trihalomethane, which is not desired. Therefore, that's another reason why do we want to convert them into these combined residuals. Okay, clear?
Yes, sir.
Okay. Reducing agents and chlorine demand of water is the difference between the amount of chlorine added and the amount of chlorine present in as a residual, either free or combined after reacting with reducing agent during some design designated period. Okay, I mean reducing agents. I already told you that there are other impurities other than the ammonia, nitrogen, which are reducing and which can also convert chlorine to other species. This is also a lost. I mean loss or wastage. Theory of disinfection. Now, how does this species destroy pathogen? First of all, chlorine, either in free or combined form, react with the cellular wall material. I mean, virus or bacteria, right? They react with the cellular wall and rupture it. Rupture means breaks it down. Rupture means breaks it down. Is it clear? So the
Yes,
chlorine
sir.
residuals breaks down the cell of the bacteria or virus. And number B, they destroy the enzymes of bacteria cells and affect energy yielding process. Therefore, the bacteria cannot produce energy anymore. Therefore, they basically becomes inactive. And number C, and possible that it actually passes through the cell wall to attack the intracellular system. Efficiency reduce. Okay, the thing is, the efficiency of the disinfection process depends on the pH as well as the temperature. If you increase the pH to 8.5, your disinfection process is better. Also, if you reduce the temperature, your disinfection process is better. Are you following me? So, therefore,
Yes, sir.
overall, if I say that disinfection efficiency increases with increased pH and with decreased temperature. Okay, okay.
Okay.
রিকমেন্ডেড মিনিমাম ক্লোরিন রেসিডুয়াল ফর ব্যাকটেরিয়াল ডিসইনফেকশন কত সময় তোমাকে পানিতে রাখতে হবে কন্ট্যাক্ট করতে হবে ওকে how much contact time you need to uh, successfully perform the disinfection process contact time In case of free available chlorine, like hypochlorous acid and hypochlorite ion, if your concentration is zero point 0.2 milligram per liter and pH is 6 to 7, you need 10 minutes contact time. But in case of combined chlorine, which is basically what? Monochloramine and dichloramine, you need 60 minutes of contact time. If you have 1 to 1.5, this is 1.5. If you have 1 to 1.5 milligram per liter concentration. Okay.
Okay.
Oh, I explained the thing in reverse way. I'm sorry. That's was a mistake. Efficiency is reduced by increased pH, and efficiency is reduced by lower temperature. That means in higher temperature, efficiency is higher. That's is a correction. I just it was a slip of tongue. If efficiency is, for example, if let's write it down in this way: efficiency is increased with increasing temperature, and efficiency is decreased with increased pH. Is it clear now? Is it clear now, guys?
Yes, sir.
Yes, sir.
Or I can write it in this way: efficiency is increased with decreasing pH. So if temperature increase, efficiency increase. If pH decrease, efficiency increase. Okay. So that's why you see your pH has increased from 6 to 7 to 8. Now you have more concentration. You need more concentration. You need more concentration. Do you see? Previously you required zero point 0.2. Now you need zero point 0.4. Is it clear?
Yes, sir.
Yes, sir.
And forms of chlorination. You can add chlorine in different forms like pre-chlorination, post-chlorination, double chlorination, super-chlorination, breakpoint chlorination. And we usually use this breakpoint chlorination. Okay. Now the thing is, there are other methods of disinfection. Chlorination is just uh, just a single method of chlorination. There are other methods of disinfection like ultraviolet ray, UV ray, ultrasonic wave, metallic ions, heat. Okay. Now ultraviolet rays, you see this in university when you try to collect drinking water. Do you see some filters are attached into the wall?
Yes,
Yes,
sir.
sir.
So they actually have three or four tubes, right? So two or three tubes has filter, and one tube has like this a bulb, and this bulb produces a ray which is ultraviolet ray. And whenever the water passes through this, for example like this ultraviolet ray passes through the water and kills the pathogens. Is it clear?
Yes, sir.
And as you can see, the maximum disinfection happens at an wavelength of 254. Maximum effectiveness you get it around 100%, which is which wavelength? 254 here. So we use 254 nanometer wavelength to kill the pathogens. And this is a schematic of the tube, schematic of UV unit with cover removed. Okay, so inlet, you can see the inlet here. So water passes through this, and they get uh, they are in contact with the ultraviolet ray, and then which kills the pathogens actually. Okay, any questions, guys?
No, sir.
Okay. Now the thing is, UV light is credited by Health Canada. They actually developed it, and the United States of Environmental Protection Agency (US EPA). Likewise, in Bangladesh, we have Department of Environment (DOE), which controls which is a regulatory body to imply the environmental rules. Okay, okay. Department of Environment, পরিবেশ অধিদপ্তর.
Okay, sir.
Okay, if you want to build an industry, you need a permission from the Department of Environment to make sure that your industry is not harmful to the environment, or you have taken the necessary measures to protect the environment from your industrial activities. So this is Department of Environment is in Bangladesh to protect the environment. Similarly, in United States of America, they have US EPA to protect the environment. They are the regulatory body. And in Canada, this is Health Canada. Is it clear?
Yes, sir.
Yeah.
So, what is so UV light is most effective to kill the bacteria like E. coli, protozoal seeds such as this, this, and this. You don't need to remember this name, just this. Now, most viruses and these bacteria. Because UV light is not effective for virus inactivation, the UV dosage rates must be much higher to inactive viruses. So virus inactivation এর জন্য UV লাইটটা হচ্ছে একটু weak. So you have to uh, induce much higher concentration of UV wavelength. Okay, uh, are you following me, guys?
Yes, sir.
Yes, sir.
Okay, so I think that's all for today. Okay, so any questions? If you don't have any questions, then I would like to end the lecture here.
No questions, sir.
Okay.